Hello viewers, we are into the 26th lecture. We are continuing with definite integrals. In the previous lecture what we did is the complete list of important properties of definite integrals, and today what we are going to do in this lecture is solving problems based on those properties. Those properties, as I have told you, are very important. The only thing that we must learn is to where and at what time we should use it, the occasion of using them in the particular problem. So we will be beginning with several problems, and I personally believe that those illustrative examples will make the use of those standard properties of definite integrals more easy, convenient, and it will be handy for you all to learn about those properties. We will be starting with the first exercise, as I have told you, and use of all the definite integral properties. I'll try to mention the properties wherever and whenever I am using, along with several trigonometrical results, trigonometrical ratios. If you recall, in lecture 23, I have given you a complete list and tabular form of standard angles and trigonometric ratios. Okay, so we begin with the first exercise. We are to evaluate integral I is equal to 0 to pi by 2 log sin x dx. Let me call it first, and we use the formula or the properties 0 to a fx dx is equal to 0 to a f a minus x dx. By doing so, I'll be getting I is equal to 0 to pi by 2 log, this will be sine of pi by 2 minus x dx. Remember, I am subtracting from the upper limit, so this will give me 0 to pi by 2 log of cos x dx. I'll call it second. The reason is that sine of 90 minus theta is always equal to cos theta, and therefore that is used. Next step will be add 1 and 2. So by doing that, this and this will give me 2 times integral I is equal to 0 to pi by 2 log of, this will be sin x and cos x. So I'll be having here log of sin x from here and plus log of cos x from that side. That will be dx. To be more precise, I'll be writing it 0 to pi by 2 log of sin x into cos x dx. Let me mark it third. I have used this relation. The reason it will be written beneath this, since log of m into n is equal to log of m plus log of n. That is the result, and therefore I have used it here as sin x cos x dx, and so this now will be treated as, so 2 times I is equal to 0 to pi by 2. What I do is now I'll be writing it as 2 sin x cos x and divide by 2 as well. This is dx. So I'll be getting it 0 to pi by 2 log of, this is the formula we did it earlier, minus log of 2 the whole bracket dx. I have used the formula log of m upon n, and so I'll be getting 2 times integral is equal to, this will give me 0 to pi by 2 log sine of 2x dx minus log 2 being constant, I can take it directly out of the integral sign, 0 to pi by 2, this is dx. In this particular stage, I'll call it 4. I'll be putting 2 times x is equal to some variable this. So, 2 times dx is equal to du. As we know and have discussed earlier, when we were doing the substitution for definite integrals, when we were doing the standard forms for this, the limits will be changing. So, if x is equal to 0, this one, u becomes equal to pi, the 2 will cancel. And similarly, if x is equal to pi by 2, x is equal to 0, or we can make it like this. If x is equal to 0, so u also will turn to 0, and if x is equal to pi by 2, the upper limit, I'll see that the u becomes equal to pi. So, those are the substitution and change of limit. This has nothing to do with the change of limits or substitution. So, 2I will be this 2 coming down, we will be having 1 upon 2, the u integral will have 0 to pi, 0 to pi. This is log of sine u du, that 1 upon 2 has come over here, minus log of 2, I can make it as x varying from 0 to pi by 2. So, now we will be having from this stage, I'll be going back, and from this calculation or from this step we can write here once again. So, this will become 2 times I integral on the left hand side. This will be equal to, from this stage I would like to write. So, let me repeat it here as equal to half 0 to pi log of sine u du minus, I'll bring it here, this is log of 2 will become pi by 2. So, this is pi by 2 log of 2. Let me call it as fifth. What I now use it a property, I'll be using 0 to 2a fx dx, fx dx is equal to 2 times 0 to a fx dx, because sine of 180 degree minus theta, if the function of 2a minus x remains fx, and the reason is sine of 180 minus theta is always equal to sine theta. This one, they are called allied angles, and so trigonometrical ratios, as and when we were using, I'll be giving you this result, all such important things. So, this is 2 times I is equal to, I'll have half, this will be 2 times, so that 2 which I am mentioning here is of the formula. This will be 0 to upper limits is reduced to half, so pi by 2 log sine u du minus pi by 2 log of 2. Finally, the result I am using here, now we use a to b fx dx is equal to a to b f t dt. Variables can be changed without changing the limit, and therefore, if we proceed beyond this, it is interesting to note that this particular stage, if I mark it 6th step, this 2 and this 2 will obviously be cancelling here, and so I will be using it as 2 times integral is equal to, this 2 and 2 will cancel, and I will be having 0 2 pi by 2, the original variable, log of that will be sin x dx minus pi by 2 remains unchanged, log of 2. If you recall, we have started, this was the given integral and equation first, so I can write it capital I taken from equation 1, This is minus pi by 2 log of 2, and therefore this I will be having I is equal to, this is transferred here onto the left hand side, is minus pi by 2 will be log of 2, no constant of integration. That concludes the first exercise. You might have seen the use of trigonometrical ratios of allied angles, that is 90 minus theta or 180 degree minus theta of all sine, cos and tan, and we have seen the use of two properties, the property which we did in the previous lecture. The second question, the second example using properties, I will be having this to solve, 0 to infinity log of x plus 1 upon x, this is dx upon 1 plus x square. I will mark it as 1 to start with. I will be putting x is equal to, because of this, x is equal to tangent of theta, and therefore I will be having dx is equal to sec square theta d theta. Limits will be changing. If x is equal to 0, theta is equal to 0. If x is equal to infinity, theta is equal to pi by 2. You can see the whole table so nicely written. When we were into the 23rd lecture, I gave you a broad table showing angles from 0, then we have 30 degrees, 45 degrees, 60 degrees, 90 degrees and 180. So the integral now will be converted to, this will be equal to 0 to pi by 2. This will be log, I will have it as x is equal to tan theta, so I will have it as tan theta plus 1 upon x, means I will be having again tangent of theta. This dx will be sec square theta d theta upon 1 plus x square is again sec square theta. Need not to explain much, because 1 plus tan square theta is equal to sec square theta, and therefore I have now 0 to pi by 2 log of, this will cancel automatically, and I will be having this as tan square theta plus 1 whole upon tangent of theta, and that is d theta here. Proceeding further on this calculation, this tan square theta is nothing but sec square theta. I will be writing in the same way. So integral is equal to, this will be 0 to pi by 2. This is log of sec square theta within the bracket upon tangent of theta and d theta. So I will be having it as 0 to pi by 2 from here. This is sec square theta, so I will be having 1 upon cos square theta. and this will become sine theta upon cos theta. So I can write it log of, little directly, 2 times 2 sine theta cos theta d theta. What I have done is, this you can easily follow, what I have done is I multiplied by 2, I divided by 2, this 1 upon cos square, and this tan theta will sine theta upon cos theta. The sine theta going up will cancel and will leave you like this. So this will become then 0 to pi by 2 log of, is very easy, the trigonometrical well-known formula sine 2 theta d theta. And so integral will now be log of 2 outside 0 to pi by 2, this is d theta minus 0 to pi by 2 log of sine of 2 theta d theta. I have used the formula log of m upon n, that was in the previous exercise also, is log of m minus log of n, which we all know and very easy to understand. One is log of m upon n, the second that you can understand is log m upon n. Now what I have is a very simple thing, log 2 and all that. So I will be having it as integral equal to, this is log of 2, and after integration will give me pi by 2. Okay, as simple as that. So this is minus integral 0 to pi by 2. I am solving this. This will give me log of, I break it again, and will give me 2 times sine theta cos theta. Is an important step to note, and therefore I will call it as equation 3 in continuation. That is the third part we can have. This is equal to, writing it precisely, pi by 2 log of 2. Look in here, there are three terms, 2 sine theta and cos theta. So I'll break everything, and I am using the formula log of mn, breaking into the sum. So this is minus 0 to pi by 2 log of 2 is a constant which we will take later on, d theta, minus 0 to pi by 2 log of sine theta d theta, minus 0 to pi by 2 log of cos theta d theta. I have taken everything out. So this will be equal to pi by 2 log of 2. This will also be the same. I'll have pi by 2 log of 2 and minus. I will not solve beyond this because we know how to solve it. We know how to solve this also, and these we have done just now. So either you can do it by parts, or even you can apply the property. So solve by property. This is left as an exercise. These will be cancelling. I'll be having the results only based on this. Third exercise now. We have integral is equal to 0 to pi by 2 log of tangent of x dx. Let me call it equation 1. I am using the property. This is invariably used mostly. 0 to a fx dx is equal to 0 to a f a minus x dx. Is that okay? That is the property we have used, and as I have told you, invariably we will be using this property. So integral now changes to 0 to pi by 2 log tangent of pi by 2 minus x dx. To solve it, allied angles again, 0 to pi by 2. This will give me log of cot of x dx. This I will be calling second. I write for your reference. The reason is tangent of 90 minus theta is equal to cot theta. Tangent of 90 minus theta is this. I'll be adding number 1 and 2, so I write here add equation 1 and 2. What happens is the same thing, the first exercise that we did in this lecture. 2 times I will be integral 0 to pi by 2 log of, this will become 10x cot x is easy, log of 10x and cot x that I have here. I'll be adding these two, log of 10x and cot x. I have used it by this formula, log of mn is equal to log of m plus log of n, by which I got finally this thing. Of course the dx will be there. If you recall, tangent is the inverse of this, and therefore very easily we can write that 10x into cot x will reduce to 1, because if you recall, cot of x is equal to 1 upon 10x, or in other words you can say that 10x is equal to 1 upon cot x. So this will become 1. 2 times integral will be equal to 0 pi by 2 log of 1 dx, but log of 1 is 0, and so this is 0, implies the value of the integral will be equal to 0. To remind you, had we not known these properties, we would have taken log of 10x as the first function, unity as the second function. We would have solved it by parts with all those lengthy calculations, and this property or the use of property makes many problems which appears to be lengthy in a very short manner. But it is not a shortcut, I tell you, but the calculations are reduced, and the use of property or the smart use of property will make the question looks elegant. We take up the fourth exercise. We need to solve 0 to pi x sin x dx whole upon 1 plus cos square x, calling it first equation. The same property I am using, 0 to a fx dx is equal to 0 to a f a minus x dx. By doing so, integral will change to 0 to pi. This will be pi minus x, this will be sine of pi minus x here, upon 1 plus cos square pi minus x dx. At this stage, I must tell you that since sine of 180 means pi minus x, as I have seen, it is sine x. We were solving the question just before this, where we have seen this, and another allied angle will be having cos pi minus x is equal to minus cos x. Remember these, but since it is a square, will make no change, will remain plus, and therefore I'll be having from here integral is equal to this is 0 to pi. I'll be having pi minus x into sine x, obvious, upon 1 plus cos square x dx. Let me call it equation 2. the same thing. After using this, usually we have seen in the last 3 exercises that we add them. So I add first and 2, left hand side will become 2i. So I write here add number 1 and 2, and therefore 2 times I will become 0 to pi. As you can see here, this x will cancel with that x, sin x is taken common, so I'll be having pi sin x, pi is outside, so this will become sin x upon the LCM that I'll be having 1 plus cos square x dx after adding. So that will be the third. Pi is taken outside. We will be put cos of x something as v that we can put, and so sin x dx is equal to minus dv. That is one part. Limits will be changing. If x is equal to 0, v is equal to 1, and if x is equal to pi, v is equal to minus 1. To advise you, please refer to lecture 23 if I am very confident about it, and you can see the table form given for standard. So cos of 180 is minus 1. 2i continues, and therefore 3 leaves with this 2 times integral is equal to pi will remain. For 0 I will have this, for this I will have minus 1. This will become dv with a negative sign outside, 1 plus v square. That is easy now. This is the final that I have. But at this stage, if you recall, we can apply another very important property. That property is that if there are limits which are having the same value, the sign can be altered, and therefore I will be having 2 times integral is equal to pi. This will become minus 1 to plus 1 dv upon 1 plus v square. I'll call it fifth. I have used the property, if you recall, a to b fx dx is equal to minus times b to a fx dx, meaning thereby that if the limits are interchanged, lower becomes upper and upper becomes the lower limit, the sign of the integral changes, and therefore this result is arrived at. I can use it minus 1 to, so I am using further minus a to plus a. This is another property that I am using. Fx dx is equal to 2 times 0 to a fx dx, provided if f of minus x is an even function fx. But here you can see that is minus of v whole square remains v square is an important property. So using all these 3, the fifth becomes number 5 implies 2i on left hand side continues. I'll be having it here 2 times pi. This 2 is because of the formula. I'll be having 0 to 1. Nothing changes here. 1 plus v square. I hope from here it appears that you can guess how we are going to get the answer for it. And in doing so, I'll be having, first let me cancel it out. 2 cancels on both the sides, as you can see here. So integral is equal to, this will become pi tan inverse v, the standard form, that will be 0 to 1, and this will be equal to pi tangent inverse 1 minus tangent inverse 0. You know, tangent of 1 is nothing but pi by 4, that is 45 degrees, and tangent of 0 is equal to 0. From here it's very easy. So integral becomes pi, and this will become pi by 4, and so the result arrives at pi square upon 4. We will be taking another exercise couple of more to make it more clear, so that we can see the applications. Thank you, viewers, for listening to these all solutions, and take care to solve further more problems.